Okay, so looks like our class size keeps shrinking. So you can make it to the end. So random forests were the culmination of the last lecture. We learned about trees, and we learned that trees, individual trees, when you let them be deep, have a lot of leaves, they can pretty much fit anything, but that's not great because you can perfectly fit your training data and then still not do well in your test data. But then we learned that we can combine them with ensembling and get some really robust high performance methods. So the idea here is that you train trees typically with a limited complexity, but then you train many of them, maybe hundreds of them, in parallel, making them diverse by giving them either different features, restrictions to use different features, and or random subsets of data. And then they end up looking sufficiently different, and then you basically average over all of them, and then you get a nice method called a random forest. So in terms of, so these work pretty well out of the box, but then you can tweak them a little bit better, and there's all sorts of different parameters that you can use to tweak them. Like obviously the number of trees is going to be one parameter you use, but many other things about how the individual trees are designed, like exactly how deep they are, how many features they can use, et cetera, et cetera. So for your projects, that's kind of what you'll need to do, is play with a lot of those parameters, learn, try to understand a bit more about how these trees work. And I'll post some resources, or maybe I'll include them in the notes, that get into some of the important parameters to tune if you're trying to make a random forest work as good as possible. Okay, but I won't talk more about them now. So today we're going to talk about boosting, which is training ensemble methods, often trees, sequentially rather than in parallel. So the intuitive idea is you start out by designing a tree like you always do, just to minimize, if you're doing classification, you'd minimize probability of error. But then you look at what happened in that first stage of design. You look at the particular data samples where you made mistakes, and then you train a new model that puts a higher weight, higher emphasis on those bad training examples. And then you see how it does, and then you essentially look at where its errors are, and then you put higher weight on those, and so on and so on. And at the end of the day, you get a sequence of different models, and you train them so that when you add them together, they're a really good model. So this is principally different in the sense that you have to train them one at a time based on the previous ones, and so it's a sequential method. So AdaBoost is one of the most famous early methods from the 90s, and that was generalized to gradient boosting in the early 2000s, and then that was kind of perfected or enhanced for XGBoost, and there's actually a few other ones which are maybe even slightly better improvements, slight improvements over XGBoost that happened more recently. But we'll talk about these three. They'll give you the flavor of how these methods work. So some notation. So we are going to design an ensemble of predictors, FM. So you can think of each of these Fs as like a tree. And again, we do this sequentially, so you can imagine there's a for loop starting with m equals 1, the first tree, or sometimes we say the first stage in this boosted predictor. So we're going to train FM to minimize a weighted loss. So this is some loss. You can see that depends on Y, the training, the label, and then F, the prediction. But here's the weight. So you can see the weight depends on the training sample I, and you can see the weight depends on the stage of boosting that we're at. Okay, so you train a predictor to minimize its weighted loss, and then you evaluate that predictor on the training data again, and you choose weights that you will use in the next round, and you just repeat. Train a predictor, update the weights for the next time, train a predictor, update the weights, and so on. When you're all done, you have a set of predictors, and you might also have a set of scalar weights that you apply to each predictor so that when you add them together, you get this capital F, which is the boosted predictor. And this is the capital F after capital M stages. Okay, so this is what we're eventually going to use as our main method, this capital FM. Okay, and we are going to focus for this derivation, we're going to focus on binary classifiers. And we're going to focus on predictors that always return either 1 or -1. So they're not returning soft estimates, but hard estimates. And there are versions of this that are, have been derived for regression, non-binary classification, but just for simplicity, we're going to focus on this case. Okay. So any questions so far? No? Okay. Yeah.
Just a clarification. So the weight in this, it's not like a future weight, it's just a weight of the...
This alpha?
Yes.
Yeah, it's just a number for it's just a scalar value, positive, typically positive value for every stage. Basically just, it's like you're doing a weighted average and it just says like how you're going to weight the different predictors together.
Okay.
So it will be something that we optimize when we, along the way as we design. So now we get into the details, I think it will be more clear. So we're going to focus on binary classification. This is our training data as usual, and the training labels, of course, are going to be plus minus 1. And we're going to design these base classifiers, little fm. And so this is how we'll do it. We're going to define the step little m boosted classifier as this capital F little m. And to get that, we just take the previous capital F and we add alpha m times fm. So it's like essentially we're building this up recursively. We start with alpha 1 and f1, and we'll initialize at 0. So like f0 will be just the 0 function. So we'll have capital F1 will be alpha 1 f1, capital F2 will be alpha 1 f1 plus alpha 2 f2, capital F3 will be the first 3 of these added together, and so on. Okay, so that's what this boosted classifier here gives us. And then at each stage, well, this is basically a summary of the process. So we're going to initialize this boosted guy at 0, like I said. And then at each stage, we're going to design a positive weight and our intermediate classifier FM so that the overall boosted predictor at that stage minimizes the exponential loss. So let's take a look at this loss and understand why this is a reasonable loss to use. I don't think it's a loss we've seen before, but so okay, as all losses, it's just summing over our training samples. And let's consider what happens. This is classification with y is plus or minus 1. So let's consider what happens when we're correct. So when we make a good prediction of the label yi, this should have the same sign as the label yi, right? Whether yi is positive or negative. And so as a result, this product, yi times capital F, should always be positive whenever we don't make a mistake. And when this is positive, we're exponentiating something negative, which means that this value is below 1, right? And the larger this is, when it's correct, the larger this is, the smaller this is. So, it doesn't add much to our loss. We get a big addition to our loss when this capital F has the wrong sign of y, because then the thing we're exponentiating will be positive, and then this contribution will be greater than 1. and so on. So it's a very convenient loss just because it has such a simple form, e to this product. So I think that's mainly why it's being used here. It's just really easy to work with. Okay, so that's our goal, is to minimize this exponential loss. And we try to do this at every stage. So this is what we do at the little nth stage. Okay, so given that, so here's the exponential loss, where all we've done is we've plugged in this equation for f. So we get this inside that loss expression. And now we have e raised to the power of one thing plus another thing, so that we can decouple that into e raised to this times e raised to that. Right? So here's e raised to the first thing, and then this is e raised to the second thing. Okay. Now, what's nice is that since we are designing little fm at this stage, this is what we have already designed at the previous stage. So this is not something we're designing now, it's something we know. So essentially for this design stage, it's just a constant. I mean, it's a known quantity. So as a result, we can compute this thing, and we can just think of this as a weight. It's a weight that applies for stage M and sample I. And then this is the thing that we now need to really focus on, because we are trying to design the alpha and the f here. Okay, so we'll just call this WMI from now on. And yeah, it's a weight because when you look at this equation, you can see this has the same form, but there's like a weighting WMI applied in front of the exponential. Okay, so the next thing we can do is we can break the sum into the I for which our little f has the correct sign, or is correct, and the I for which our little f is incorrect. And remember that yi and f are either 1 or minus 1. So when y and f agree, that means that this and this can just be removed, right? Because they're both 1 or both minus 1. You just remove them from the expression, after which we get e to the minus alpha. In the case that they don't agree, because they're plus or minus 1, then we can remove their product and replace it with minus 1, which cancels this, and then we get this thing. So it's a nice simplification. And that's the second stage. Now, another thing that we can do to maybe make this look even a little bit more intelligible is notice that this is a sum over I, whereas that exponential doesn't depend on I. So let's actually move the exponential to the front. So we're going to put it over here. E, sorry, that doesn't look like an alpha. Looks like a D, but it's should be an alpha. Okay. Okay, and then now we can get rid of this. Okay. Now the next step is to essentially take some of these quantities and move them back into this sum so that this sum is over all the I. It's maybe one way to think about it. Or another way to think about it is, let's complete this sum by adding in all the other terms in I, but then subtracting the same terms again over here. So what we need to include is all the I for which this is true, with those values of the weights. And as you can see, they will all be multiplied by this. So essentially, we're going to cancel that by subtracting that same quantity over here. Right. And then what's here, that part is just what we had before. Okay, is that pretty clear? So the reason we're doing all this is because now what's cool is that we have isolated the thing we are trying to design let's say f, into this term alone. This is not a function of f. This is just this positive scalar when we design f. So we can just focus on this part alone for designing f, and that's pretty simple. Okay. All right, so let's see. Any questions so far? Okay. So this is the thing we want to design. In terms of interpretation, this is just a weighted misclassification loss. Imagine that all the weights are 1, which is actually what we're going to do when we start out. Then we're just summing up all the times that we made a mistake, right? So that's just number of errors. And now it's a little different because the weights are not 1, so sometimes when we make an error, it's going to count more or less than 1, depending on what happened in the previous stage, because these weights are completely determined by this value from our previous stage boosted classifier. Okay, so that's why we can think of this as a weighted misclassification loss. And there's a couple ways to write it. You can write it with this complicated sum, or you can write it with a regular sum, and then you have this indicator variable which turns on whenever you make a mistake, becomes 1, and if you did not make a mistake, then this turns off and you have 0, and then you're not including it because we don't want to include that in the sum. Okay, so just a couple different ways to write this in case this one looks strange to you. Okay, so what happens at step 1 is we're going to set all our weights to the value 1. That's how we initialize it. And then if you think about training that first predictor, we're just training to minimize number of errors or maximize accuracy. So that's how we've always trained things for classification. So that's what we do for our very first stage. Now, once we've designed that and we move on to the next stage, step m greater than 1, then we compute these weights, which essentially measures how badly, it measures whether we made errors or not. And when we made errors, you can see that now for the next stage, we're going to count those samples higher. We're going to say, pay more attention to those. We made an error on those last time, so try not to make an error on them again. And then that's how we train our next little f. Once that's trained, we add it on to our, this is like an accumulation of the scaled little f's and so on. Okay, so we haven't talked about the alphas, but we also have to design the alphas, but that's kind of in spirit how we do the f's. We're always training f to minimize some sort of weighted misclassification loss. Any questions on that? Yeah.
When we're designing little f, is that just like moving the decision boundary, or like what are we adjusting with that f?
Oh, typically it's a tree, a regression tree. So yeah. So I guess when we talked about designing regression trees, let's see, or classification trees, we didn't explicitly talk about minimizing error. We talked about like doing things like splitting for homogeneity reasons, But eventually, when you do that and you get these like perfectly homogeneous leaves, then it is, we don't know if we're going to minimize classification error exactly, but we're going to get some classifier that has as a goal. So yeah. So I think we can just think of it that way, like just design a tree as usual. Yeah, but I don't know. I'm not a super expert on trees. People don't seem to really use them that much anymore. At least they're not things people are doing research about. So it's a good question. I actually haven't really thought, like if you actually want to design a tree to minimize classification error, could you do that, or is it always some surrogate? Like you're minimizing something else and then hoping you are minimizing classification error. something like that. But it's a good question. Okay. Um, so let's say we've designed F. Now our objective is to design the alphas. And to design the alphas, we want to minimize the same loss. And and this is our expression. So for this, alpha is just a scalar variable at this stage. So it's pretty straightforward, right? We know how to do that. This is differentiable in alpha. So we take the derivative of this expression, set it to 0, and solve for alpha. Simple as that. And when you do this, I didn't include all the steps, but you get alpha of this form, where this epsilon, you can interpret as a weighted error rate. So let's see what we mean by that. So imagine that all the weights are 1, which is what happens in the first stage. So then this is exactly the error rate. It's a number between 0 and 1, where you're counting up the number of places you made a mistake over the total number of samples. Now, when the weights are not 1, it's a weighted error rate in the sense that some of the samples, when you make a mistake, you're counting them, more or less than 1, just depending on how these weights are adjusted. And then this is like, relative to the sum over all the W's. So again, this will be a number between 0 and 1, but it will just have a slightly different interpretation than your standard error rate. Okay, so pretty much that's it. So just to summarize, we initialize the weights at 1 initially, and then you compute, you design your predictor, so maybe it's a tree. Once that's designed, you evaluate this weighted error rate, epsilon, then you plug that into here, you now have your alphas, and now based on your previous predictors and your newest little f, you can update your boosted predictor. And once you update that, the last step is to update your weights according to that equation. And then you begin again designing each one of those in turn. Okay, so that's how we do it. Once we're all done with capital M stages, we have our F capital M, that's our final predictor. Now when someone gives us a new test sample X, we just put it into that, and whatever comes out is going to be our classified outputs. Notice that the outputs of these are not going to be plus or minus 1, because essentially they're a weighted sum. This is, sorry, let's see. Okay, this is a weighted sum of things that are plus minus 1, right? So this is not necessarily plus minus 1. So, but we do hope that the signs are correct. So whatever the sign of this capital FM is, you want it to match the sign in Y. So you just focus on the sign of that, and then that's all you need for a classification. Okay, so I think, I think that covers all the steps. So making sense? AdaBoost? Okay. So AdaBoost is it's a really neat idea, but it's kind of limited. Like in this case, we really exploited strongly the fact that the labels were plus minus 1, as well as F outputting plus minus 1. And it's not exactly clear. And we also exploited very much this particular exponential loss. If we didn't have that, it's not really clear you could do this derivation. So, and there are certain ways to extend it, but it's not very general. So that was sort of the motivation. Oh, actually, we'll do an example. But that was the motivation for this next approach, gradient boosting, which tried to be much more general. But let's just look at this example. So when you go to sklearn, you have AdaBoost classifier and AdaBoost regressor. By default, the predictors that it uses are 50 decision tree classifiers, so there's 50 stages. And these are classifiers of depth 1. So when a tree has depth 1, you call it a stump. Okay, so they're very simple. So here's a picture. So this is the first iteration. This is your training data. You have a class of blue pluses and a class of red minuses. And so your objective in that very first iteration is to design a stump that tries to minimize classification error. So a stump is basically going to be a partition into 2 boxes horizontally or 2 boxes vertically. That's it. You just get to pick one threshold on one of the 2 axes. So in this case, given that data, to minimize classification error rate, it's maybe not exactly obvious what to do, but perhaps this is a good choice. Let's say for this, on this side, we got all of those right. We could say that for the minuses, we got all of those correctly classified. And then for the pluses, we did make some mistakes here. These are correctly classified. So certainly not perfect. So now in the next iteration, or to prepare for the next iteration, we would look at where we made mistakes. So we made mistakes on these guys. So these guys would get a higher weight. And that is represented here by the fact that these increased in size. So they were weighted higher. And then meanwhile, these guys get a lower weight. And so they get these smaller fonts. And because the weights, if you think about the weights at the first stage, it's either going to be 1 over E or E, right? Because these are going to be, at the very first stage, either going to be 1 or minus 1. So some got bigger, some got smaller. Okay. So the next stage, we have a classification problem now where we want to pay more attention to those particular samples. And so this time, maybe we pick this classifier, this stump, because it's going to get these right, and it's actually going to classify all the minuses correctly, but it's going to make some mistakes. Oh, sorry, it's, is that right? It's, yeah, the pluses are all correct. The minuses, we're going to make a mistake on those minuses. So those guys, their weight increases for the next stage, whereas the weights on all the other ones that we classified correctly, they decrease. Okay. So, and let's say we stop there. So now we have these 3 classifiers. Simultaneously, we have gone and designed our alphas, which let's say gave us those numbers. And then when you put all these together, you get a much more interesting classifier. You can't quite see the weights, or can't see the heights of the different regions, but you can see what the regions are, and the regions are doing a perfect job of classifying our test data. Even though the individual predictors were extremely simple. Okay. Any questions on AdaBoost? Okay, so gradient boosting is next. So here, our objective is to minimize a loss of this form. So here you can see L. We want this to be a bit more general. This is the label YI, as usual. This is the boosted predictor after M stages, as usual. The boosted predictor has the same form as before. We have some alphas, we have some little f's. And these little f's are going to be within a family of predictors F. So for example, if I'm designing, maybe I'm going to constrain them to be decision stumps. So this would be like the class of all decision stumps that I could make. So I'm constraining them to be of a particular form. And when we did this with AdaBoost, we had to use a particular loss, which had this form. And we had to use FM that ensured plus minus 1 outputs. And so now we want to be a bit more general. We're not going to force this, and we're not going to force the use of this loss. So that's the goal here, to handle general loss and general structures of predictors. Okay, so if we could, this is how we would like to proceed. So at the very first stage for little f, we would find a little f within our allowed class of predictors that minimizes the loss on our training data. Once we've done that, we're going to set capital F1 equal to our little f1, so this is our first boosted predictor. At our next stage, we are going to say that, let's say F2 is going to be this F1 we just designed, plus this will be like alpha m times little fm xi. Okay. So, but now in particular, we want that the product alpha m times little fm, when added to the previous, so this gives us our current fm, we want that our current capital FM minimizes our loss. So this is, even though we're designing this kind of update to it, we want that the boosted predictor at this stage is optimal in terms of minimizing our loss. We do that by selecting alpha M and FM, and once we have selected them, then this just shows how we add them to our previous boosted predictor to get our current boosted predictor. Okay. So this is what we would like to do, but this problem is often too difficult for generic losses and predictor architectures. So we can't attack this directly, so we're going to make an approximation. Instead of looking for an exact optimization, argmin, why don't we consider a gradient step? Like, imagine we can compute a gradient, and then we can move in the direction of that gradient to minimize, to not perfectly minimize or optimize, but like to decrease the loss. Right, so that's the idea behind gradient boosting, is rather than exact minimization, settle for a gradient step. Okay, so, but again, this is a little bit tricky. So if we're going to do that, then that would say that our new capital F equals our old one minus a step size times a gradient. And so here we would need to compute the gradient of our loss, this overall thing, with respect to, at the location of where we were. So this is compute the gradient at our old capital F. So, so the one trouble here is, if let's say you could compute this. Well, if you compare this expression to this expression, that means that this gradient here would be your new little f. But we said that our new little f was actually constrained to be in some function class, like maybe it has to be a stump, decision stump, or something. And there's no way, we'd be very lucky if when we computed this gradient, it gave us a function that could be implemented as a gradient stump, right? It's probably not going to be some other function. So we can't do this gradient step exactly. So instead, what we're going to do is we're going to try to design FM to get close to this, as close as possible. So we have the gradient is now going to be our target. That's what we want little fm to be. And we'll train little fm to be close to the gradient. And so it's kind of like two levels of approximation. First, we said we'd like to do this, but we're going to approximate it as a gradient step. And we said we can't actually do the gradient step exactly, so we're going to approximate the gradient by some other thing that is as close as we can make it to the gradient. Okay, so this is sort of what I was saying. This is what we have to do. This is what that strategy is telling us to do. And we can't equate them exactly, but what we could do is we could train this to be as close, or train this to be as close to this as possible. Okay, so in particular, let's define the gradient. This is actually just the derivative of our loss with respect to the prediction. Right, so this is just going to be like our y hat, basically. So this is nothing more than dl dy hat. And we're going to call that, people call this the negative residual, minus r. So this is going to be something that depends on stage m, and of course, it depends on the ith sample. So that's why you have an m and an I dependence. And we're just going to give this a name, minus RMI. So that means that we want the output of FM, if I plug in xi, to be close to minus RMI. That's the goal. So we'll just train it with this new loss. So here we're trying to force the output of our predictor, given xi, to be close to this gradient. Okay. So we have the gradient, that's our target. We design a predictor that's giving us something close to the gradient. Now, that hasn't told us yet what step size to use, right? This is like a step size times the negative gradient. So let's figure out the optimal step size. We can actually just do this because we have a training data set. So we know what this is going to be. This is something we already designed. This is something else we just designed. And now I can find the alpha that is optimal in minimizing our loss over all our training samples. That's just like a grid search. You just have a grid of alpha. You find the alpha which works best. We'll call that alpha M. And now we're done. Now we have the scaling or the step size. We have FM, and we boost our predictor to get our new predictor, and we start over. So that's what gradient boosting is, and the main nice thing here is you can use any loss you want, and you can use any predictor, family of predictors you want. Could be trees, could be neural networks, could be whatever. Okay. So any questions on the derivation? Okay, so one thing that people find in practice that makes this less prone to overfitting is even though we went through all this work to compute the optimal step size that minimizes the training loss, they actually make it smaller. They put in this mu, which is something between 0 and 1, to actually say, let's take a smaller step. And that's going to mean we're going to have more stages, but that helps with generalization, better performance on the test data. So that's what's done in sklearn gradient boosting classifier or gradient boosting regressor. By default, they're using 100 decision tree classifiers of depth 3, and by default, they're both using mu as 0.1. Here. So here's a little illustration. There's two different green traces. It's a little hard to see, but what we have here is we have a regression problem with the scalar x, so scalar feature x, and then this is the target y, scalar. And so if you had a regression tree of max depth 1, how many, so that's going to be a simple curve. That's going to be this. Does it make sense why this has 2 levels? Why it looks like a step function? Yeah, because this is a regression tree of max depth 1, there's one split. So they've made for this tree, they made a threshold here, and then they trained a value if it's less than that, and they trained a value if it's greater than that. And in both cases, the ground truth, the target, is this blue smooth shape. So that's sort of like the best fit of the blue shape to any kind of step function. Okay. Now we could do this for a regression tree of max depth 3. How many different levels can I get from that technique? 8, right? Because I can split once into 2, and I can split each of them, and then I can split them. So I get 8, and there is another green, lighter green curve of here. So this is 1, 2, 3, 4, 5, 6, 7, 8. And as you can see, that is a better fit to that blue curve. And then in red, it's showing gradient boosted regression trees of max depth 1, but there's possibly many stages. So like the simplest one is this one. That would be single stage. I think, yeah, that's single stage. Now, if you have 2 of them, let's see, that's probably, I don't know exactly where it is here, but maybe it's this one. It's hard to say exactly, but as you boost more and more stages, you get down to this final bold red curve. And as you can see, that is a much better fit than any of these. At every stage, it gets to be a better and better fit to the blue curve. And finally, it gives you something that is certainly not perfect, but it's close. And of course, the design never knows the blue curve. It just gets these training samples, right? That's all it gets. And as you can see from those training samples alone, it's pretty hard to figure out where that blue curve is, just limited training samples. So it does a good job, given the data it has. Yeah. And this is from some, can't remember, maybe that's, can't remember exactly if that's online or a paper or what, but basically there's other nice tutorials about this stuff if you're interested. Okay, so that's it for gradient boosting. Any questions? All right, so the last technique, XGBoost, is a pretty famous technique because it, at least until recently, I don't know where things are exactly today, but like it was sort of like the de facto method people would use for machine learning contests, just because it works so well on so many problems. Not for images, but for like lower dimensional tasks, very generic tasks, whether it's prediction or classification. When you talk about images, then you really, you have often like hundreds of thousands of pixels. You want to do things with convolution and so on. Trees are not the best approach for images. But when you're working with just what they call tabular data, just generic data sets that you find online, XGBoost just out of the box gives you really good performance. So what is XGBoost then? Okay, it's very similar to gradient boosting. It's basically an evolution of it. Rather than just looking at computing a gradient, it considers a second-order Taylor series approximation from which you can get a gradient but also a curvature. It uses regularization. We'll see. It uses a pretty sophisticated tree search and many parallelization and hardware acceleration tricks. So I'm only going to talk about the first of these. I'm not going to talk about this at all, but you can, if you want to read the paper, it gets into a lot of details about that stuff. And XGBoost, not exactly sure why. It might be licensed by some university or company, but it's not part of sklearn. But you can download it for free, like an Anaconda. And it has exactly the same interface as sklearn. So, you're familiar with sklearn, you know exactly how to use XGBoost. You can just use it in your notebook as if it was part of sklearn. It has GPU support. It has all kinds of stuff. Okay, so this is how it works. So it's going to design a boosted predictor that looks like this. Notice, similar to what we've done, but no alpha m's to worry about. And similar to gradient boosting, we would like to do this. So you have some loss, L, which is going to be generic here. You're training your first little f to just minimize the loss on the training data, and then you set the first big F at that little f. Then you go through stages, m equals 2, 3, 4, and so on. And at every point, this is the loss with the boosted predictor you will get after you design little f. So this part was what we said the goal was for gradient boosting. It was too hard of a goal. We had to take a approximation, but that was the goal. That's also the goal here, except we're going to add a regularization term. The regularization, as we know, is there to help fight overfitting. And so this has a very particular regularization, which we'll see in a moment. But as before, this optimization problem is too difficult to solve exactly, so we're going to have to do some approximation. So we're going to take a second-order Taylor series approximation, like fitting a quadratic. Not really fitting a quadratic, but just you guys know what a Taylor series is. And it's going to be on this loss term. So it's basically saying the loss evaluated at capital F, which is what we know, plus this little f, which is something we're trying to design, can be approximated by the loss just at the capital F, plus the gradient times this perturbation little f plus the second derivative times, actually it's not even the gradient, it's just the first derivative, because this is a scalar. And let's see. No, this is going to be a gradient. Never mind. Okay, this is a gradient. And then this is going to be the second derivative here. Okay, so sorry, whether this is a gradient or a derivative just depends on whether this capital F is a scalar, whether y is a scalar or not. So I guess sometimes it could be a gradient if y has multiple values, but if y is a scalar, then this is just a derivative, so this is just a scalar. Let's just assume for now this is just a scalar. So we have, this is just a scalar derivative of your loss, and then this is the second derivative of your loss, and this is your squared perturbation. So hopefully you recognize this as just a Taylor series approximation, first and second derivatives. So once we make that approximation, we're going to replace this with this term. But then we realize that if we're designing little f, we don't have to worry about this first term because it doesn't impact us, so we can just focus on the sum of the second two terms. So that's what we have here. And then we have our regularization as before. Okay. So our objective is to find this little f that minimizes this. Okay. So now we're going to be very specific about the structure of f. We're going to say it's a decision tree with a maximum of capital L leaves. And we learned that we can think about decision trees as sort of a two-step process. The first step is like a lookup table. So we're going to call Q the function that takes in a vector of features and outputs the leaf of the tree that we're on. So that's the lookup table. And then the second stage is for that given leaf, or this is the lookup part of the table, and then this is the table part. For that leaf, you say, okay, which output will I give that leaf? Okay, so we're just giving explicit names to the part that tells you which leaf you're on, and then the part that tells you the output value to report for that leaf. Okay, so basically ZL is the predictor output assigned to leaf L. Here, ZQX is just saying X goes to leaf, goes to label. Okay, everybody good with that? Just a notational thing. All right, so this is the regularization that's used for XGBoost. So the first part you can see is a sum of a squared, it's a summing over all the leaves, summing the squared value of the outputs. So it's actually just clamping down on the outputs, trying to push the outputs towards the origin. And there's a tunable lambda that we need to adjust here. And then there's also a regularization that affects how many leaves are on the tree. So the more leaves we have, the larger this regularization gets. Okay. And so basically, this is enough to do the rest of the derivation now. So we want to minimize this. And so what we need to do is we need to write this. Instead of writing this over the sample index I, we're going to write it in two stages. We're going to sum over all the leaves indexed by L. And then we're going to have the second sum as all the samples that give you leaf L. Okay, so this is summing over the leaves, summing over the samples that give that particular leaf. So what that allows us to do, oh, and we're also going to omit the M notation here just to keep things simple. So this becomes GI here. This becomes ZL because we're saying explicitly that L is the leaf for which that XI landed on. So this is just going to be ZL. This is just going to be HI because we're omitting the M. And this is just going to be ZL squared. And finally, for the regularization, we have that already in the form of ZLs and everything we need. So we just copy that directly. Okay. So now the things we have to design are the queue, which is kind of how we split the tree, how we make that whole tree structure. And then second, how do we come up with the labels ZL? Okay. So let's tackle the ZLs first. So all we need to do is essentially just rewrite this in a cleaner way that's going to look at the ZL term, all the ZL squared terms, and the constant terms. So there's only one term with a ZL. So we have essentially two sums, GIZL. So here you see the two sums, GIZL. There's actually two terms with a ZL squared. So the first one, we'll say this is the first one. We have two sums. Sorry, we just have this. We have the sum over L times lambda times ZL squared. So here's sum over L times lambda times ZL squared. And then the other one here is a sum over L and I and HI. So that's sum over L, sum over I, HI, and we have the 1/2 from here. Okay, and then the very last thing is this, but we can actually put this lambda here inside the sum over little l, and that will just give us finally the lambda times big L. Okay, so this is our new objective, and now you can see we've kind of partitioned it into a cost for the elf leaf. This is the cost for the elf leaf. And what we can do is we can optimize over ZL, over each ZL. So if I'm optimizing over Z1, that means I can just focus on this. I don't have to consider any of the other leaves. And we know how to do this. You just take the gradient of this with respect to Z, set it to 0, solve for Z. And when you do that, you get this nice expression here. So it involves a sum, sum over the I that gave you that particular leaf, and then these GI, HI things which we computed from before. So these are the optimal Z's. You take this expression, you plug it in to here, and that actually will simplify this, and that brings you down to this problem. So now the ZIs have been selected, but what's not selected is that tree. We have to design the tree Q. Q is the whole structure of the tree. And this is what we would like to do. We'd like to minimize this loss over all the leaves. Okay, so this seems a little bit complicated. How do you even attack this? So essentially, we can attack this the same way that we designed trees before, this top-down procedure. So imagine that we're starting from scratch, and we're just designing the very first stage split in our tree. So essentially, we have a data set S, and that's the whole data set, whole training data set, and we're trying to figure out how to split it into two. And we want that after we do the split, we're only going to have two leaves, right? So we want that the cost summed over those two leaves is as small as possible. So this is what the cost will be before we do the split. Then we just have essentially one leaf, you could say. Sort of trivial. So you would just evaluate GI and HI over your whole training set. You get this value. So that's if you do no optimization. Now, once you design the split, you're going to have two leaves when you're done. And this will be the cost component for the first leaf. This is the cost component for the second leaf. And the way they differ is just in the subset of samples I. So this is samples corresponding to the first leaf. This is samples corresponding to the second leaf. Okay. So in essence, this is now your homogeneity criteria. So previously when we designed trees, we talked in terms of homogeneity. This is essentially just, if you want to interpret this as a type of homogeneity, that's what it is. But it's this whole top-down thing where every time you design a split, you have a problem of exactly this form. All that changes when you do it is the exact S's you start with and the S's you end up with, right? So you start with your entire training data set and you split this into two. Next time, this is S1 and this is the split of S1. Simultaneously, this is S2, this is a split of S2, and so on. And you keep splitting those up further and further. So is that pretty clear? Yeah.
Is the split done like for each feature?
That is, well, so whenever we design trees, we always threshold one feature at a time, right? And we always have to decide which feature we want to threshold, as well as what the specific threshold is. So those are the two things we have to decide for every split. And so, there's sort of the exhaustive way of doing it is you consider all the features and all the possible thresholds for every feature. And then there's shortcuts where you say, I'm going to randomly draw a few features for this stage. I'm only going to consider them. And so in this case, I don't think you're necessarily going to be doing that. I think you're going to be using all the features, but it could actually be that I would think maybe XGBoost gives you the option. You could look at all the features, or you could, do bagging or whatever way of subsampling you want. My guess is all those options are there. Okay, so, but this is how we do it. So of course, the next question is, well, how do you know when to stop? How do you know when to stop splitting? Well, that actually, you can get that from the cost. So you want that the cost decreases after you do a split, right? Well, what you can do is you can look at the difference in the cost before and after. That's what this difference is. And ideally, this should be a positive number, right? Something big minus something smaller. But if you find after your best split that this thing is negative, it's a sign that you shouldn't do any split at all, because splitting only hurts you. It only makes your cost bigger. So that's exactly how you know when to stop. Down any path of the tree, you compute this, and whenever the loss gets worse, you stop there and you move on to some other branch of the tree. And eventually you stop everywhere and you're done. Okay, so essentially that's it. That's all I wanted to describe to you guys. There are a lot more tricks, especially in hardware and stuff, that are in the original paper. But it's a really great method. And I don't have a demo for anything in this unit, but you can find, like this is an example of what you need to do, and it's so easy. It's exactly like sklearn. You instantiate the classifier, you do model fit, model predict, that's it. Same thing for the random forests. You can find examples of them on sklearn web pages and stuff. But like I said, there's all kinds of parameters that you can tweak for these, and there are various articles people have written, and I'll share some of the better ones I found that say, like, okay, this is what you do to win the machine learning contest. You look at these first, you try with these, and then you try with these, and so on and so on. And so that's really the kind of the hard part. It's very easy to get good performance with a tree, but then getting great performance, beating all your classmates, essentially, that requires work and ingenuity and trying to understand, what's actually going on under the hood of these trees. So I'm not going to lecture anymore. This is the end of the unit. But for those of you on the project team who are doing this, you'll have to go a little deeper and read some articles and try to understand what's happening with these trees. How can I really maximize the performance? Okay. So that's it for this unit. Any questions? I hope to get the project posted by the end of the week, but right now I'm grading your midterms. I'm almost done. So, all right. See you guys on Friday. I'll pass out the midterms on Friday.